Welcome to Lecture 14 of Electrical Engineering 525. In this lecture, we'll look at three problems. The first one will be from section 6.5, which is on loaded wire antennas, and the last two will be from section 6.6, which is ground plane backed wire antennas. And this should be a relatively quick lecture, I believe, because all of these problems are relatively straightforward. So let's jump right in. For the problem from section 6.5, we'll look at 6.5-1. In fact, that is the only problem in your textbook concerning this section. And it goes as follows. It says a monopole is embedded in a large dielectric medium with relative permittivity of 3.4. Determine the length in free space wavelengths of the quarter wave monopole if the wire radius is classified as thin. So the first thing we need to do for this problem is to see what they mean about the wire radius being classified as thin. And the answer to that is in table 6-2. In 6-2, you see wire radii classified as very thin, thin, and thick. And for the thin classification, what that means is that the shortening that is required for a dipole that is classified as thin is 5%. That's 5% shortening that is required because of the fact that the radius is non-zero. You know, what I'm saying here is that for our theory, we developed the theory for infinitely thin wires, but then when we thicken the wire in order to maintain, remember what we were trying to do here is to have a real input impedance, and we can achieve that by shortening the dipole, and the amount of shortening that is required for a wire that is classified as thin is 5%. A different amount of shortening would be required for very thin or for thick antennas, but for one that's classified as thin, the amount of shortening required is 5%. So since the amount of shortening that is needed in this case is 5%, then that means that we want the resulting length of the monopole in this case to be 95% of what one would initially expect. Now, keep in mind that this is supposed to be a quarter wave monopole. So in other words, if it were infinitely thin, then the length would be lambda over 4. But since it's not infinitely thin, instead it is classified as thin rather than infinitely thin, then we want it to be 95% of that length. So the proper length should be 0.95 times 0.25 lambda. Now, I've written this as lambda sub d because this monopole is embedded in a dielectric, and so the wavelength that we must use here is the wavelength of light in that dielectric. In different dielectrics, radiation will have different wavelengths, and so we must use the wavelength that is appropriate for that particular dielectric. So we have 0.95 times 0.25 lambda d, and so the final answer is L is equal to 0.2375 lambda d. That's the number of wavelengths in the dielectric that we want for the length of this quarter wave monopole embedded in the dielectric of relative permittivity 3.4. However, the question was to determine the length in terms of free space wavelengths. So the final step in this problem is to convert this length, which is given in terms of dielectric wavelengths in the dielectric. We need to convert that to wavelengths in free space. And so that's the question that's posed right here. It says, how is lambda d related to lambda naught, the free space wavelength? Okay, well, the way to answer that question is to remember our formula that f times lambda is equal to the speed. And so f times lambda d is equal to v d, and similarly f times lambda naught would be v naught, where v naught would be the speed in vacuum, and v naught, of course, is also frequently referred to as c. So, sorry for the sound effects from the dog there. Okay, so we have f lambda d is equal to v sub d, and that's equal to 1 divided by the square root of mu d epsilon d. Mu d here is the permeability of the dielectric medium, and epsilon d is the permittivity of the dielectric medium. Well, mu d is the same thing as mu r times mu naught, where mu r is the relative permeability of the medium, and mu naught is the permeability of free space. And epsilon d is the same thing as epsilon r times epsilon naught, so where epsilon r is the relative permittivity of the dielectric medium, and epsilon naught is the permittivity of free space. So we have this formula, and then we can break up this radical in the bottom to the square root of mu r epsilon r times the square root of mu naught epsilon naught. And now coming down, just bringing down the f lambda d on the left-hand side, and we can rewrite this term here on the right-hand side as 1 over the square root of mu naught epsilon naught divided by the square root of mu r epsilon r. And the reason for rewriting it that way is that we recognize that 1 over the square root of mu naught epsilon naught is c, the speed of light in free space, and the speed of light in free space is the same thing times f, the frequency times the free space wavelength, so we can substitute that for c, and so we have f lambda d is equal to f lambda naught divided by the square root of mu r epsilon r. And so if we cancel the f's on both sides, then we have the answer that we want, that the wavelength in the dielectric, lambda sub d, is equal to the wavelength in free space, lambda naught, divided by the square root of mu r epsilon r, where once again mu r is the relative permeability of the dielectric, and epsilon r is the relative permittivity of the dielectric. Now, we're not told about anything about the permeability of this dielectric, and therefore that means that we're supposed to assume that mu r is equal to 1. Whenever we're not told, we're just assume that mu r is equal to 1. And we're also told that epsilon r is equal to 3.4. So if we plug in mu r equals 1 and epsilon r equals 3.4 into this formula, then lambda d is equal to lambda naught over the square root of 3.4. And so lambda d, if you do this calculation, lambda d is equal to 0.54 lambda naught. And therefore, if we return to our earlier calculation, remember that L, the appropriate length of this quarter wave monopole embedded in the dielectric, is 0.2375 lambda d. And now we substitute that lambda d is equal to 0.54 lambda naught, and we get then that L is 0.1288 lambda naught. And so that is the final answer to this problem. That is the value for L given in terms of free space wavelengths. And that concludes our only problem for section 6.5. Now we move on to section 6.6, which is about antennas that are backed by ground plane, wire antennas backed by a ground plane. And actually, what we're going to do is instead of using a ground plane, we'll use a mesh or a grid of wires instead of an entire ground plane. And both of these problems that we'll do from section 6.6 involve that concept. So let's go ahead and move into this. The first problem says a wire grid is to pass through not more than 2.5% of the incident power. So that means that most of the power, what we have here is that the antenna is in front of this grid, and the grid is reflecting the radiation from the antenna back, and we want it to reflect most of it. We only want it to pass through 2.5% or less of the power that's incident on that grid. So we want 97.5% or more of that power to be reflected. Now it tells us furthermore that the spacing between the wires in the grid is to be 0.12 lambda, and so what should the wire radius, what wire radius is required? So let's work first with, we're going to have to use one of the figures in your book to get the final answer for this problem, but we can do some preliminary work first. Actually, let me stop this for a moment and show you what figure will be needed. So here is the figure that we will need for problems of this nature. And let's look at this. Okay, here is this little diagram. Well, you see, first of all, here 3 vertical lines, or scales, you might say, because each one is marked with numbers. And in between the second and third vertical lines, we have a little diagram here. Here are some of the wires of a grid of wires, and you should understand this is that these circles indicate that the wires are coming out of the page of the paper. And you can see that the diameter of a wire is 2a, so a is the radius of these wires. And here you see that s is the spacing between the wires. And furthermore, you see these arrows here. The first arrow here is labeled P. That's the power that's incident on the grid of wires. And you see that we have a reflected wave here, gamma squared P. That's how much of that power will be reflected, is gamma squared P. And then the amount that's transmitted is 1 minus gamma squared P. So this diagram here is meant to help you remember the situation that these lines describe, and then to look more carefully at the lines. Okay, the first line here on the left represents the spacing, that is the spacing S between the wires, the spacing in wavelengths. The middle line gives us the transmitted power in dB. Now, the transmitted power is the 1 minus gamma squared P. And then finally, the last scale here gives us the ratio of the spacing to the wire radius, and that is S over A. S is the spacing and A is the radius. And the idea here of this problem is that if we have any 2 of these numbers, then we can find the third because all three, for any particular situation, all three will line up on a straight line. So again, if we're given any two of these, then we can predict what the third should be. But again, notice that in order to use this, for instance, in the problem under consideration, remember, we were told that we want the spacing to be 0.12 lambda. So we're given this value, and we're asked to find the radius of the wires. So we want to find a value over here. So that means that we must also be given something, some information about this, but we are. Remember that we were told that the amount of transmission should be less than or equal to 2.5%. And so, and the transmission is exactly what this measures. The only problem is that this transmitted power is given in dB rather than in a percentage. So we just need to convert that 2.5% to dB, and then we'll be able to read a value from here, and we have the value 0.12 lambda over there. When we connect those two with a straight line and then extend it over here, we will get the desired the desired value for S over A, and then we can find out what A should be. So that will be our strategy for solving this problem. And so now to actually do all of that in equation form. So again, we have that the transmitted power, 1 minus gamma squared times P, should be less than or equal to 0.025 P. That's there because it said we want the grid to pass through. Pass through is the transmitted part, not more than 2.5%. So we want the transmitted part to be less than or equal to 0.025 P. Of course, the p's will cancel on both sides, and that tells us that 1 minus gamma squared is less than or equal to 0.025. And to convert this to dB, then we need to take 10 times the log base 10 of each side of this equation. So we get 10 log base 10 of 1 minus gamma squared is less than or equal to 10 log base 10 of 0.025. And when you take this, compute this value on the right-hand side, then you get 10 log of 1 minus gamma squared should be less than or equal to minus 16.02 dB. Now, let me break for just a moment, and I'll show you then how we complete this problem. So now to complete this problem, remember, now we want the spacing to be 0.12 lambda, and we have found now that we want 10 log of 1 minus gamma squared to be less than or equal to minus 16.02 dB. And so now we will turn to the figure 652. We will join those 2 points, the 0.12 lambda and minus 16.02 dB. We'll join those two and then read off the value from the third scale. And so all of that is shown here in this figure right here. Here you see on the separation, the spacing, we have marked that at 0.12 lambda, and here on the 10 log of 1 minus gamma squared scale, we've gone to minus 16.02 dB, and we've drawn a straight line, and if we extend that all the way over here to the third line, we see that we get a ratio for S over A. It looks like essentially exactly 11. And so that's the value that we will use. And it's just that simple to use that figure, 652. And so it says here, we use this to see that the ratio of spacing to wire radius should be S over A is less than or equal to 11. And the reason for the less than or equal to is because of this less than or equal to. If they had specified in the problem, instead of saying not more than 2.5%, if they had said exactly 2.5%, then all of these less than or equal to signs would be equalities. But since they said not more than that, that implies that less than or equal to is acceptable, and so that's why I've carried that through this problem. But if S over A then is less than or equal to 11, we multiply each side by A and divide each side by 11, and so we get A is greater than or equal to S over 11. S again is the spacing, which is 0.12 lambda, and so the spacing that we want, A, is greater than or equal to 0.011 lambda. And the fact that this turns out to be greater than or equal to makes sense, because you can think, the thicker you make your wires, the more reflection you would expect. And remember, that was the whole point, was we don't want too much transmission. We want no more than 2.5% transmission. So at 0.011 lambda for radius, we would get that amount. And if we make the amount any bigger, we would get even less transmission. So the fact that we end up with this kind of relationship for the desired radius makes sense. So that concludes our first problem, and now we will consider a second problem in section 6.6. For the second problem, which is problem 6.6-3, we have a wire grid is to have a reflection loss of 1 dB. What percentage of the incident power will be reflected? So when it says that the reflection loss is 1 dB, what that means, and you pretty much just need to know that, to know this, it means that 10 times log of base 10 of the reflected of the reflection coefficient, gamma squared. This is the reflection coefficient for the power. Gamma is the reflection coefficient for individual field component. Gamma squared is the reflection coefficient for the power. So 10 log of gamma squared is equal to -1. The negative sign because of a loss, and 1 because they say 1 dB. So 10 log of gamma squared is -1. So gamma squared is 10 raised to the minus 0.1 power. And if you do that calculation, gamma squared is 0.7943, which would mean that 79.43% of the incident power is reflected. And so 79.43% reflected corresponds to a 1 dB reflection loss. And that's all that this problem is about. But you do need to know this technique for one of the problems that will be on the test. And so that concludes our problems for this lecture, for lecture 14. And good luck.